So yes, standards for silicon acceleration. So we're going to be talking about some of the APIs and file formats and other standards that are at the lowest level of the software stack, underneath games, underneath engines like Unity. So everyone gets to use our stuff eventually as they go down towards GPUs and other hardware in the system. And if you haven't come across Khronos before, we're an open standards organization. We create royalty-free standards for use by the industry. And we have a particular focus on connecting software to silicon. So acceleration APIs for interesting problems, things like 3D graphics, AR and VR, vision processing, and increasingly things like neural net acceleration too. We have about 140 companies, everyone from Apple and Google all the way down to single-person startup companies. And we're open to anyone who wants to join in and help us define these standards. So what are some of the most relevant APIs to this audience? I've picked out a few. We have about 15 active standards that are in development, but we're probably best known for the ones on the right-hand side there, the 3D APIs. OpenGL, the granddaddy of 3D APIs, was originally at SGI but came across to Khronos about 10 years ago. OpenGL ES is a Khronos standard for 3D on mobile phones, WebGL for 3D on the web, and the new generation Vulcan, which we'll be talking a little bit about today. GLTF is a 3D file format that goes along with those 3D APIs. It's for transmitting 3D assets efficiently between apps and devices. And OpenXR, which is a soon-to-be released standard for cross-platform augmented and virtual reality. We have some vision and neural net processing APIs. Don't have time to go through those today, but there's lots of information on the website if you want to get more on those. So let's talk about Vulcan first, 3D graphics. OpenGL is 25 years old this year, and so it's about time for a new architecture for letting developers access their GPU. And the whole point of Vulcan is that it's much lower level than OpenGL. The OpenGL drivers that you have in your system today, and some of you might have used, are getting to be quite thick pieces of software in their own right. They're almost like a middleware engine sitting between your application and the GPU. And those drivers are getting complex enough that many developers are spending more time reverse engineering around them to try and get the GPU to do precisely what they'd want than actually getting value from that, the functionality in the driver itself. So with strong demand from the developer community, we now have these new generation of APIs. Vulcan is not the only one. DirectX 12 and Metal are the others. But their whole point is to be much closer to the silicon. You get control as a developer precisely what you get the GPU to do, which means it's higher performance, lower latency, which is great for VR. You need to understand what a GPU can do, but if you do understand that, Vulcan gives you the opportunity to make it do exactly what you want. The other big nice thing about Vulcan is it is an open standard. It's not being built by one platform vendor. So DirectX 12, which is from Microsoft, is an awesome API, but it's only available on Windows 10. Metal is also from Apple. It's also an awesome API, but it's only available on Apple platforms, whereas Vulcan is pretty much available everywhere. It's available on not just Windows 10, but Windows 8 and Windows 7, and still 50% of the world's PCs are Windows 7. Linux, both in consoles, on desktops, in the cloud. Nintendo Switch has a Vulcan driver, and Android has selected Vulcan for the new generation 3D API that's a key part of the platform definition of Android. And Android is the largest platform now in the known universe in terms of seats. The only place we can't ship Vulcan right now is Apple platforms, but actually we're working on that too. So I'll come to that in just a few slides. So how do we drive the 3D and other functionality that we need for high-performance augmented and virtual reality? So even before Vulcan, Khronos APIs have been used very widely for driving the displays. We have OpenGL on desktops, OpenGL ES on mobiles, WebGL in the browser, and that's now it's going to be, over time, replaced by Vulcan. But there's a bunch of other stuff we need to do in AR and VR. We need to be able to feed back the tracking and devices in an AR and VR system. We need to know where the HMD, the head-mounted display, is. We need to know what devices the user is using to interact with his environment. And that's what OpenXR covers. So Vulcan and OpenXR are intended to be used together. The Vulcan API is covering rendering, and OpenXR is pretty much covering everything else that you need to do in an AR and VR app. And that's why we chose XR. We're not trying to create another star R thing. It's the name is intended to illustrate that we can cope with both AR and VR applications. And in fact, the logo is a cunning A and a V stacked on top of each other. But it is true that the first version of OpenXR, which is coming soon, has a primary focus on VR, because VR is a more evolved technology in terms of shipments. There are Oculus and Vive systems shipping right now today that need this kind of standard, but we're soon going to follow up with more functionality that would be applicable just to AR, but within a common framework that lets you go from AR to VR pretty easily. So what is OpenXR trying to achieve? So on the left-hand side of this slide, we have the current situation today, and Dan was kind of alluding to this, that whether you're an app or you're an engine, there's this diversity, which is a great thing. There's a diversity of VR devices and runtimes. There's the HTCs, there's the Oculuses, and in the mobile side, there's Samsung and Android Daydream. They all have the same kind of APIs for doing similar things for the applications to access, but because they're all designed in parallel and they're being designed by different design teams, they're all slightly different, and for really no good reason other than that they were designed in parallel. Similarly, we have, again, as Dan was saying, lots of innovative new devices coming into the AR and VR space. I've seen foot trackers, eye tracking, all kinds of things are coming over the horizon. But right now, that device community face a real barrier to actually getting their devices out into the market. They have to go to each one of these runtime vendors and beg, borrow, and steal cycles from the development team. Please integrate my device into your runtime so I can actually ship with applications. So those are the two problems that OpenXR is intended to solve. The most obvious one is the application-facing API. OpenXR is defining a common API as agreed by and developed by all of these runtime vendors. So all the VR functionality you need to access as an application into the runtime, you can use a single API that all of these different runtimes will understand. Similarly, at the device layer, it's a more tricky problem from an engineering perspective, but what we want to achieve is a device manufacturer can write their own OpenXR driver and self-integrate that driver into any compliant OpenXR runtime. That means that any device can easily ship with any of those runtimes that support the OpenXR standard. So we haven't released version 1.0 of the spec yet, but we are getting close, weeks rather than months. And the good news is that we have a good set of logos on this slide. All of the GPU vendors are here. Probably most importantly, all of the runtime vendors are here. So Oculus and the Steam and Google is here. Samsung is here for the mobile side. Epic is actually the chair of this group. Google is a specification editor. So it's a good mix of desktop and mobile vendors. Even Microsoft and Sony have asked their logos to be added to this slide in support of the development of OpenXR. So it's pretty exciting to see the industry come together to solve this problem. That'll be good for everyone. So people normally ask once they first hear of OpenXR, the question is, so are you trying to replace those runtimes, all of those different runtimes? The answer is no. we're simply defining XR APIs that all these different runtimes, and there's probably going to be more over time, they can choose to expose, probably alongside any proprietary APIs that they already expose. And it's really a win-win. The runtimes that expose the OpenXR APIs will get access to more apps and to more devices. Apps can ship in more places, devices can ship in more places. So it is a win-win. So we're expecting quite fast adoption. So Vulcan is the other side of the VR AR equation. As I mentioned, the whole point of Vulcan is we take the thick OpenGL driver and really pare it right down into the minimum thinnest driver that you can use to access GPU functionality. All of the front-end compilers, all of the debugging tools are taken out into installable separate layers that don't ship along with the driver itself. So if you don't need them, you don't have to use them. And the key thing we couldn't solve with OpenGL was fundamentally a single-threaded driver model, whereas Vulcan lets you use multiple threads to prepare work in parallel and submit it to the Vulcan engine. So it really breaks the single-threaded bottleneck, which in the end was the one thing we really couldn't solve in the traditional OpenGL model. So Vulcan is interesting if you can get to it, and the good news is Vulcan is just over a year old. So compared to OpenGL, which is 25 years old, Vulcan is still just a baby, but it's already being shipped by every GPU vendor, and it's pretty much on every platform other than Apple, PCs, mobiles, consoles, embedded. Lots of the VR platforms and all of the games engines now pretty much have Vulcan support. It's getting good vibes from the developer community too. Lots of people are liking Vulcan, as you have to use Vulcan with some conviction, not just use it as a thin OpenGL if you're going to get the performance benefit, but lots of people are to that stage now. And my favorite game, every morning I get up and check the Wikipedia page, and the current score is Vulcan Games 35, DX12 Games 25. Vulcan is evolving quickly, so there's a bunch of extensions that have shipped since 1.0 back in February last year. Explicit building blocks for virtual reality, things like single call to get multiple angles into the scene displayed, so it's very efficient. Low latency, multiple GPUs, which can be useful for high-end VR. We're strengthening the ecosystem, better tools, better compilers, and those extensions will be rolled into new versions of Vulcan over time. But one of the interesting things that we are doing, the number one question we get is, when can I get Vulcan on Mac? Because I'm a game developer, I would ideally love to write once and ship on mobile, Android, and Windows, and Mac, and iOS. So, for business reasons, Apple are not currently letting us deploy Vulcan natively on their platform. So we came up with an idea that we talked about at GDC, which was, well, let's create like a subset of all three and create like an amalgam API, a fourth API that could run everywhere. And the developer community, I'm sure perhaps some of you here gave us the awesome feedback was, that's a terrible idea. Please don't do that. 3 APIs is bad enough. 4 APIs is even worse. And of course, that was the correct feedback. So we went back to the drawing board. And instead now, we're working on what we call the Vulcan Universally Portable subset, which is standard Vulcan. But if you're careful and don't use some of the more advanced parts around the corners, there's actually like 85% of the API can be very efficiently mapped onto either Metal or DX12. And we have enough tools, compiler tools, cross-translation tools between HLSL, Metal Shading Language, and GLSL now, that we can also take the shaders in and out of the different systems. So we think we're actually pretty close to having a shippable system where you can take a Vulcan program, if you're careful and just use the subset, which is a pretty big subset, you can have native performance across a bunch of different platforms. So watch this space. There might be some stuff at GDC where we talk about that. So these are the native APIs. Of course, the ultimate portable platform is the web. Anywhere you find a web browser that supports WebGL, you can literally run your whole app without changing a single line of code on a bunch of different platforms that have compliant browsers. In the history of the world, there's never been such a portable platform as the web. And the web browser vendors are to be congratulated and thanked for this. They put an enormous amount of work into bringing their WebGL engine into the basic stack of the web. So the WebGL 3D engine now sits alongside HTML and JavaScript and CSS as a fundamental part of the browser, which can be accessed through JavaScript or through middleware. WebGL is built on top of OpenGL-ES, and if you look at the evolution, what we've had up until a few months ago was WebGL 1.0, which was based on OpenGL-ES 2, which in turn was developed in 2007. So that was 10-year-old technology. It's good 3D technology, but it's very much mobile-based technology. The exciting thing happening as of a few months ago, March 2017, WebGL 2 launched, being supported in an increasing number of browsers. Soon will be very pervasive, and that's based on OpenGL-ES 3, which is basically desktop class graphics. So WebGL is transitioning right now from mobile capabilities to desktop capabilities. And the browsers, again, are putting a lot of effort into making this portable and reliable across different browser implementations. So now there's an interesting question, and we don't quite know how it's going to work out. WebGL needs to run on top of an API that's available everywhere. OpenGL-ES 3 was the last universally available API. Apple did not ship ES 3.1, which brought compute shaders, which a lot of people want. And now, of course, the web wants access to this new generation of explicit APIs. So the Vulcan Portability Initiative might provide a universally portable API. There's also some discussions in W3C, and so we'll see how that works out. But WebGL 2 is here. I think that's really the message. If you're looking to replace Flash for interactive games and ads, WebGL is the way you want to go. Adobe actually said that explicitly when they announced EOL for Flash. And WebGL 2, you can see down in the bottom left, is already about 60% web browser availability, and that's just after a few months after launch. So give it another 6 to 12 months, I think it's going to be pretty much everywhere. Microsoft, so Google and Mozilla are already shipping in their production browsers, and Microsoft and Apple are saying they're going to ship very soon. And once that happens, WebGL 2 capability will be pretty much everywhere. It's interesting to see how the ecosystem stacks up, because we want to bring VR and AR into the web too. So how is that going to work? It's interesting to look at how the native stack piles up, and that will give us some insight into perhaps VR and AR is going to come to the web ecosystem. So if you look at the native stack, you're writing a native C or C++ game or app. You can certainly use these APIs that we've been talking about, OpenGL, ES, or Vulcan, or OpenXR, if you're doing AR or VR. But of course, in reality, most people don't. Most people would go through an engine like Unity or Unreal. And again, Dan mentioned some of the engines out there for AR. There's AR Core from Google. There's ARKit from Apple. Vuforia is an AR engine that's more industrial based. And they will layer between you and those bottom layer APIs. So what happens in the web space? Well, there are certainly web applications out there that write directly to WebGL, which in turn layers over OpenGL-ES. But again, most people would tend to use an engine. 3.js, Babylon.js are very common engines that are used, that are kind of like provide you nice functionality, kind of like Unity in a native space. You can also use Unity to generate WebGL apps. So I think as we go to VR and AR in the web, we're going to find the same kind of pattern. WebVR is an experimental API coming out of W3C. It layers over WebGL and OpenXR and provides you a lot of the VR functionality similar to OpenXR. We're actually working very closely, WebVR and OpenXR. OpenXR is going to save the WebVR guys a lot of time Because at the moment, the WebVR guys are trying to port individually onto all these different virtual reality systems. We can save them all of that busy work. And we're already finding more layers of middleware building on top of things like 3GIS and WebVR to bring easily authored augmented reality and virtual reality into the web stack. There's more work to do on how we actually expose functionality like AR Core and AR Kit in the web stack. Mozilla has some experimental projects underway. They're calling it WebXR. If you want to look it up, it's very tentative, but soon over the next year or two, I think we'll begin to see how AR is going to appear in the web stack as well. But I think we'll continue to see this layered approach where JavaScript higher levels in the middleware will layer over the lower levels native APIs. Last thing I want to cover quickly is GLTF, which isn't an API. It's a 3D file format for transmitting 3D assets to applications. It originally came from sending assets to WebGL, but now with GLTF2, we can use it for transmitting assets to any of these underlying APIs. And GLTF2 has cool materials. We have PBR rendering, physically based rendering. So you can define with a few parameters lots of cool materials and have them render accurately and consistently across different platforms. So this boombox, for some reason no one understands, has become like the de facto standard for cross-platform rendering. So this boombox is now rendering on GLTF, on WebGL, GLTF on Vulcan, on DX12, and Metal. And it looks the same. A big ecosystem of tools coming to now beginning to export GLTF directly, and an increasing number of engines importing GLTF directly. All the ones you probably know and love are probably there. One of the interesting ones is Office. You might have noticed that PowerPoint now has 3D, and they're using GLTF to import 3D models into Office. And Microsoft also built a GLTF exporter for Minecraft, which is interesting. And again, another logo field, but a lot of good 3D companies active in the authoring and the engine field, really putting their support behind GLTF. There's no rocket science in GLTF. The key to GLTF is that everyone's agreeing on the format rather than creating their own format. Everyone's kind of created their own up to now. We can save ourselves a lot of work and get ourselves a lot of synergy by all agreeing on one format, and that's GLTF seems to have that momentum. So Khronos is, I mentioned at the beginning, an open consortium. Each one of these APIs is developed by a working group. So all the members come together. Those that are interested in, say, OpenXR come together in a working group. Those working groups produce the specifications and the tests and documentation, education materials, and anyone is welcome to join as a member and help us develop these. We have things called advisory panels, which is zero cost, invite only. If you're interested to come and help advise some of these standards, you're welcome to approach us. And we're trying to do more and more in open source. So even if you're not an adopter or a member, you can still see, in many cases, what's happening, and you can provide us feedback on the web. So that's a brief overview. Hopefully that was interesting. Some of the native APIs out there. Again, a call to action is feel free to join in some level that's appropriate to your company. We would love to have your participation. Thank you.
So I'm at Microsoft. We've been using, we've been trying to get some animation data with GLTF format. And so far we've only had success with the Godot engine. We haven't been able to get bone skin meshes to work in Unity yet with GLTF. Is there any work being done on that side, or is that more of a question for the Unity guys?
Yeah, no, there's a lot of work on animation and getting it all to hang together. And actually it's Microsoft that's driving it. Sarab and the team there are actually driving it along with Adobe. So there's a lot of subtlety in both how we define the file format and how the tools and engines like Unity and others actually use things in practice as well as in theory. And we actually have a pretty good conversation ongoing to get all the details to actually fit. And GLTF is one of the standards we are doing completely in the open. So the GitHub, the GLTF GitHub just Google it, it'll come up. The discussion is on the GitHub issues, so if you're interested, you can take a look, and if you're able to contribute, please do. Yeah.
All right, thank you, Neil.
All right, thank you.